In the last example, we see that derivative is basically just a rate of change. If the value of y depends on x and x goes up by 1, then y is gonna goes up by about 1 times derivative. This is kinda true in the general sense as well. If we have y depends on x and x goes up by about the x, if x changed by about the x, then the change in y is gonna be just the derivative y prime times the x. In other words, I can say that the change in y, which is dy, is going to be the same as y prime times dx. Now, there are two ways that we can think of this equation. One way that we can look at this equation is that I can just move dx to the other side. So I'm going to have dy by dx equal to y prime. So this is the derivative notation that we used to have. Or alternatively, I can think of dy. This is the change in y. dy is the change in y, and this dx is the change in x. This is the change in x. Let me actually rewrite this a little bit. dy is my change in y, and dx is my change in x. And this y prime here is the derivative. So what that means is, if the value of y depends on x, the change in y is going to be just the change in x multiplied by the derivative. Now then, when we have a multi-variable functions now, let's say that my function f depends on both x and y, and the value of this x and y change at the same time. What is going to be the change in the value of my function? Well, we have this formula here, and this is basically just the general form of what we have earlier. The way that we can interpret this equation is that df, which is the change in f. The change in f will just come from the change in x and the change in y, and the change in x is going to be just the derivative times dx, which is the change in x. So my dx here, this is the change in x. And then I'm also going to have f sub y, which is derivative with respect to y, times dy, which is the change in y. So let's kind of see what this means in this example here. Let's say my function is just x times y. So then I can find derivative with respect to x, and that's going to be just y. The derivative of this thing with respect to x is going to be just y. So then if I want to find fx of 80 and 50, I'm going to plug in 80 for x and 50 for y. So I'm going to just get 50 here. On the other hand, if I want to find derivative with respect to y, I'm going to just get x here. So then if I want to find f sub y of 80 and 50, I'm going to plug 80 in for x and 50 in for y. So I'm just going to get 80. Now then, if I want to find df, if I want to find this df, which by the way is called the total differential, then I can go ahead and use this formula here. df is going to be just partial derivative with respect to x, f sub x times dx, plus partial derivative with respect to y, f sub y times dy. And because I have already found the blue thing f of x earlier, and I have found the pink thing f sub y earlier, so then I can just plug that in. I'm gonna have that my df is gonna be just y times dx plus the pink thing, which is gonna be just x times dy. So this is gonna be my total differential for this function. Now I want to find this df when x is 80 and when y is 50. So if I were to do that, my df at 80 and 50 is gonna be just 50 dx plus 80 dy. And let's kind of see what this means in context then. Let's say I have a rectangle and the width and the height of my rectangle is 80 and 50. So what we have here is a rectangle, and I can think of the width as my x, I can think of the height as my y, and I can think of the area of this rectangle as just the value of my function f, which is going to be just x times y. And currently the value of my x is 80 and the value of my y is 50. So that 80 and 50 is the number that we have from earlier. Now for the first part, I'd like to find the change in the area if the width increased by 1. So I have this rectangle, the width is 80 and the height is 50. So you can kind of imagine if the width increased by 1, I'm gonna have this little strip that has area 50 being added to my rectangle. So the change in the area here is just gonna be 50. And that's kind of what we have from earlier, and that's kind of what partial derivative with respect to x mean. That's how fast my area change with respect to x. If my x, which is the width here, goes up by 1, then the value of my function, which is the area, goes up by about 50, and that's kind of what we have here. Now for the next part, let me actually move my rectangle to the side here. For the next part, I'd like to see what will happen if the height increased by 1. So once again, I have the same rectangle. The width is 80 and the height is 50. Now, if the height goes up by 1, then I'm gonna have this little strip, and you can kind of see that the area of this orange thing is gonna be 80. So the change in the area is gonna be 80 now. And that is what we have from earlier as well. This f sub y, partial derivative with respect to y, is how fast the value of my function, which in this case is the area, change when the value of my y goes up by 1. And for the last part, the width and the height of my area now both goes up by 1. So I will have the same rectangle, 50 and 80. But now both the width and the height of my rectangle goes up by 1. Now then, you can kind of approximate the new area, the orange strip that I have. It's gonna be just the sum of the two that we have from earlier. And that's kind of why in the formula that we have here, we're gonna add the change that results from the change in x to the change that results from the change in y. So, if we were to look at this, I can approximate that the area is gonna change by about 50 plus 80, which is gonna be about 130. So that's gonna be approximately 130. Or if I want to do the math, I can basically just multiply 81 to 51. So I'm gonna get 4131. So the area is actually gonna go up by 131. So that's approximately 130. Notice that this 130 also corresponds to what we have from earlier as well. So if the change in x, which is dx, is 1, so if my little dx here is 1, and my little dy here is 1, so that means the width of my rectangle goes up by 1, and the height of my rectangle goes up by 1. Then the change in f, the change in the area of my rectangle here, is going to be approximately about 50 plus 80, which is kind of 130 that we have from earlier.